All right. Oops, I didn't write down what I was talking about today. Okay. Okay, so today we are today we're going to just finish up a few more slides ahead on power electronics. The main sort of bulk of it was last time, giving one example of this rectifier, which sort of does weird things to the signal, kind of distorts the normal sine waves you see, just these nonlinear elements, and for that reason, a lot of the power you actually see in homes will not be a sine wave. I'll mention two more things. So I had my little list here of different types of converting between different types of power. So we had AC, that's just as transformers, actually not power electronics typically, because it can be all still linear components. But then rectifiers, inverters, and buck boost converters for converting DC to DC. This is sort of how you do the other conversions. We talked about the rectifier in some detail, but I'll just mention the other two, inverters and buck boost converters. There are other ways of doing DC conversion, by the way, too, but these are sort of the typical power electronics way of doing it. And then the main part of this lecture will be starting our third unit of the course, which is the unit on control. So control relates now to how do we go from just talking about optimization problems in a static setting, like maybe predicting stuff, but we're just predicting one day ahead or something like that, or doing things like optimal power flow where we're allocating power, but we're doing it really in a kind of a one-off scenario, sort of a static scenario where you just have these are the loads you have, this is the cost, and satisfy that. In reality, the situation is that most domains have some sort of temporal aspect, right? Where you need to not just plan for right now, but also for an hour from now or 2 hours from now. You need to take these things into account, deciding what to do right now. And I'm using the term control here very broadly to mean things, tasks where there is a temporal component you have to take into account, essentially. So how do we optimize the system or somehow determine what a system should do when it has some sort of dynamics that preserve over time and when we have constraints over time. So of course, we'll talk about that in much more detail, and including kind of an introductory overview today, but then the rest of the course is really going to be about control. This is hugely important, of course, because almost all real-world tasks are temporal in nature. We don't have typically the case where there's just a single cost to all the generators right now that doesn't ever change, that has no constraints about what their current state is, etc. And so we really need to take into account things like how fast generators can change, what are the dynamics of power over time, how do generators actually work in terms of spinning up or spinning down their actual physical rotors. So. And there are many more things, like even like heating a room, for example, right? There's going to be dynamics there because the current temperature of a room will affect the temperature the next time. So what we'll do today, and probably next time too, on Thursday too, is just talk about a few simple examples, and that will kind of set up the rest of the course for talking about control algorithms. And in particular, I should mention, we're going to talk about control in terms of optimization. Like we do for most things in the class, we're going to really focus on the optimization formulation of control. But just to finish up this little bit here, we spent a lot of time going through these rectifiers, right? These are ways of converting from AC to DC, and what we saw was that this little configuration here will, if you don't have a capacitor here, will always put kind of the positive portion of the sine wave through that to that load element there, and if you have the capacitor, that'll kind of store some energy so that essentially this sees almost a constant DC voltage at the end. So the interesting thing, though, of course, was that when you look at what happens over here, this circuit here will draw current only when the voltage on the capacitor is less than the voltage of the source. And so that's why you get those very weird patterns like we saw in our little demo last time, where you get little blips of current and little blips of when you're drawing power from the system, versus most of the time in that sine wave you're actually not drawing anything, because the voltage is lower here than it is across the capacitor. Okay, so essentially this is the first introduction to these power electronics that we're going to see, and really we're not going to see too much more, but there are the opposite things too. So you can do the same, or not the same thing, but there is a similar circuit that will convert DC power to AC. That's called an inverter. And inverters make use of a circuit element called a switch. And this is very sort of abstract here. In reality, how you implement the switch is very dependent on the precise task at hand. You typically implement them with transistors. And so the transistor you would use depends a lot on sort of the actual domain you have. But essentially, a switch is conceptually a very simple thing, right? It's just a switch. It is sometimes it is a little element we draw like this. Where's my pseudo pointer here? Here it is. It's a little element we draw like this, just sort of keeping in mind a switch, right? They can be either open or closed. And the idea is by opening and closing these things in the right order, we can cause a lot of very interesting effects. And a simple one would be an inverter. So suppose we have a DC source here, and we want to convert it to an AC signal. So we want this resistor here to experience an AC-like signal. Well, a very simple way of doing this is, this is called an H-bridge inverter, is to just have 4 switches like this, and you alternately open and close diagonal opposing switches here. So if these 2 are closed, then current will travel like this through it. And if these 2 are closed, and I should say, if these 2 are closed and these 2 are open, current will travel like this. And if these 2 are closed and these 2 are open, current will travel like this. Okay, so in one case it's going this way through the resistor, and one case it's going this way. And that, that might not quite seem like AC power, because it doesn't look like AC power. It looks like this, right? It looks like sometimes you have a maximum voltage there, and then the maximum voltage is the other way. Because all we're doing is we're just opening and closing the switches to make the element see current in one way or the other way. Right? But that is, in some sense, I mean, you can sort of imagine, right? This, in some sense, is an AC signal. It's just not a sine wave. It's a square wave. But it is an alternating current signal. Now, to make it an actual sine wave, it actually isn't that much more complicated. You need a few more things. You need some capacitors, as you might imagine, right? You want to store some current. So if you put some capacitors there, it'll actually look much more like a sine wave, because instead of immediately taking the voltage here, the voltage will sort of be produced, will be given by the capacitor for a little while, so it'll kind of slowly ramp up. Now, you can't get a nice sine wave with just capacitors here. What you actually have to do in practice is switch these switches at much higher frequencies than just off or on. You actually kind of switch them sort of at different frequencies, and you change the frequency, and you add capacitors in a way that and then you can imagine by doing kind of both those things in the right way, you can get something that looks more and more like a sine wave. That's essentially what they do. They just sort of have higher frequency switches there, and some capacitors that smooth this thing out to look more like a sine wave, because you typically want a sine wave when you talk about power in the electric grid, right? So for example, most solar panels will have something like this. Not like this, but like the nice version of this, right? Because solar panels naturally produce DC current. They don't produce AC current, unlike a big AC generator. And so, but yeah, I guess if you were to design things from scratch using just solar panels, you probably would just design everything to work with DC in the first place. But given that everything in houses and buildings and the whole grid uses AC power, expects an AC voltage source, you have to convert them to be these solar panels to give an AC voltage or an AC current. And the way to do that is with an inverter on each of these things. So solar panel array will typically have an inverter on it, and that will convert the DC current there to an AC signal.
Is that pulsating signal PWM?
Yes, so PWM is a standard pulse width modulation. Essentially, it means any kind of signal that goes off and on.
So it's a broad category.
Yeah. So PWM can refer to any signal that looks like this. And what that is in this case is that is the signal that will control those switches. It's not the signal of the voltage itself. So it's important to distinguish between the signal that you give here, which is referred to the PWM signal. That is the signal that you send the switches. And oftentimes you will send them something like this, where first send them a small blip, then a longer blip, then a longer blip, like that. And by doing stuff like that, by varying the actual duty cycle of the PWM, you can get different effects there. This is sort of all tangential, not tangential, but this is all kind of more than we're actually going to discuss in the course. But essentially, this is the PWM signal, and that is the signal that's used to control the switches themselves. That's not to be mistaken for the actual voltage or current that comes out of the system. That is not a PWM signal. This is the PWM signal. It just basically means you sort of control it by changing the time this is on versus off, and that is the pulse width. The width of the pulse is essentially is the control signal you give. So that's where that's where you might have seen PWMs. If you see that term, they're just talking about changing essentially the width of these little pulses you send to the switches. And we'll actually, in the next example, also talk about a system that uses PWM signals to control it. So this is the sort of we went through the AC to DC case. This is the DC to AC case. And the last thing we're going to talk about is DC-DC converters. So how do you convert from one DC voltage to another? And this is also going to require switches. At least the way we're going to do it is we're going to require switches. But before I do that, actually, I just want to point out that it's actually very easy to step down DC voltage, right? So step down at least. It's harder to see how you step it up. But if you have a DC source here, and you have some resistor, right? And you want that resistor to see, and this is 10 volts, say. This resistor will see a 10-volt drop across it. So that will also be a 10-volt difference, right? If you were to add another resistor, though, up here, say the exact same kind, then half the voltage drop would come from this guy, and the other half would come from this guy, right? So this would only see 5 volts. So we've now stepped down the voltage to be 10 volts across this thing to just 5 volts. And of course, a different amount of current will flow through it as well, because different amount of current, the total resistance here is twice, and so half the current will flow through. Now, this is a very wasteful way of converting DC voltages, right? Because essentially, the way you do this is you are just burning up half that power. If I were to do not this, if I were to do just this, somehow change my voltage of the source, then this element, say this, and maybe this is a light or something like that. This is the one that you want to be using power on. This would use up all the power, whereas if we had the resistor there, we would only be using half the available power, right? Half of it would just be being turned to heat essentially, and if you don't want heat, maybe this is an air conditioner or something like that, you probably don't want to be generating half your power to heat. So essentially, it's pretty easy to step down DC voltage at least, but this is very kind of wasteful. And a lot of things, a lot of DC voltage controllers that you will see, though they aren't quite this bad, are actually work similar to this. So like linear voltage regulators, for example, are also very, if you've heard that term before, that's great. If you don't worry about it. But essentially, they don't quite do this, and actually they don't do this at all. But what they do is something that still effectively burns up some amount of power and dissipates it to heat in order to control the voltage at the end. Okay, and so this is in general sort of very wasteful. And there's also no obvious way to step up voltages here. It's not clear how you would actually increase the voltage rather than just here I can put an extra element here, but I can't put less elements there than nothing. So how do I increase voltage? And in fact, this is sort of one of the big reasons why AC historically got so popular at the time. When it was built, there was no easy way to step up DC voltage to very, very high levels. And so because of that, AC was very nice because we know we can use a transformer essentially to get very high voltages. Those can go across transmission lines. They have very little loss then, and everything's nice. DC couldn't be transmitted long distances without that. What we have now are ways of stepping up and down DC voltage with at least theoretically no loss. And of course, there is some loss in practice. But that has to use these power electronics, has to use switches that switch at very high frequencies to do it. So DC-DC converters, they also make use of switches. And the ones, at least the ones that sort of theoretically don't have any losses associated with them, typically use switching at very high frequencies, like 10 kilohertz or so. So this is much faster than anything we've seen before. The H-bridge, for example, I guess if you had like the fast PWMing, that can go faster too, but just the H-bridge that just sort of make the square wave, that's switching at 60 hertz, right? So this is much faster than that we're switching here. And here is and there are two kinds that I want to mention. I'm not going to go through the theory of these at all. You should just be familiar with that they exist, and maybe if you want to take a course on this later, there's lots of courses here on power electronics, so you can write the equations for this, and they're actually quite simple, the equations for how these things work, but we're not going to get into them here. But what they are essentially is they are a combination of inductors and capacitors, and diodes too, but the diodes basically just make sure that nothing kind of, the current never flows this way, for example, which actually could happen if you don't have a diode there. But essentially they're these systems with a switch and some capacitors and inductors. And at least theoretically here, there are no resistors before the load. And so in theory, nothing you do here other than consume power at the load here will consume any power. So in theory, these are actually lossless ways of changing voltages. So let me sort of describe intuitively how this works. And this is still something that kind of is tricky to get sometimes, but what they essentially correspond to, and I think the best way of understanding that, this is called a buck converter. This steps down DC voltage. We'll see in the next page a boost converter, which steps up DC voltage. But a good way of sort of thinking about these is as ways of kind of regulating current flow almost. And we're going to use this inductor here to regulate current that flows through the inductor. Okay, so imagine if this switch was closed. Okay, so this switch is just closed all the time. Well, then, at first the inductor would block some of the current, but eventually it would just start flowing through. This would act as just a wire, and so this load here would see the full amount of voltage. It would see that this is 10 volts. It would also see 10 volts. If the switch is open, then it won't see anything. Obviously, it'll see 0 volts. And the idea of a buck converter is that if you switch that switch very, very fast, it'll kind of be in between those two. And you'll see actually a lower voltage across this thing. Now, importantly, there's no loss here. So when you see a lower voltage, that means you have to have a higher current flowing through this guy. Okay? Now, the way this actually works, and this is a little bit confusing, the way this sort of works is actually, one of the best ways of analyzing it is to analyze the current through the inductor, which is not the same as the current through this guy, but it's the current through the inductor. And what happens there is that essentially, when the switch is open, the current starts dropping through that, because there's some current going through it, and it wants to kind of drop down a little bit. When the current closes, when the switch closes, the current starts going back up a little bit. And so you kind of regulate the current flowing through here to some intermediate value between the full current that would flow through and the other current, and the current that would go through if it was just, or no current. Now, in order for the current to actually do that, this has to do interesting things with voltage. So actually what it does is when the current's flowing through, there's a little bit of a voltage drop there because there's not, it's not acting as a, it's not as if it's an open circuit, so there is going to be a voltage drop across this. When it's the other way and this thing is open, the voltage drop actually reverses itself. And you get actually higher voltage here than there. So this is sort of confusing, but essentially if you write down what's going on, you integrate these equations and you smooth it out, what you'll see is that on average, the voltage you see here is just going to be equal to the proportion of time the switch is open versus closed versus open. So if you set a signal like this to the switch, where here this will be closed, or 1 will be closed, closed, and 0 will be open. Again, if it was always open, that would be 0 voltage. If it was always closed, it would be whatever voltage you see there. If you go like this and sort of send a very, very fast signal, like this, then the voltage, I guess, across the load will be equal to just the portion of time it's on, so which people call the duty cycle, times the voltage at the source. So essentially, by having it sometimes open, sometimes closed, you can get the voltage to be at intermediate values. And don't actually worry how this works, because it is a little bit counterintuitive, right? Because the current flowing through here is not the same as the current flowing through there. The capacitor will provide the current, will provide the voltage source in the other cases, and so it's important that this is not. It's not as if you're just regulating current through the whole circuit. You're regulating current through this guy. But essentially, intuitively, I think the two cases there make a lot of sense, right? Essentially, if it's always closed, then you know that it's going to have the same voltage here. If it's always open, it's going to have 0 voltage. And by closing it, sometimes opening it, sometimes you can get a value in between. Essentially how it works. The next one, which is the boost converter, is, at least to me, much less intuitive. And there, I don't really have a good intuition quite like that, of just percentage of time being closed or open. What this does is actually will convert DC to a higher voltage. And I guess it's doing a similar thing, of course. But here what's happening is that if this, so we essentially switched the position of a couple elements here. So now the inductor is before the switch. The switch is in parallel with the rest of the circuit. So here now, if the switch is closed, well, there'll be a short circuit here. So current will just keep building up more and more and more through this thing, right? So actually, nothing really happens if the circuit's always closed. But at least in theory, you can imagine that current is going to keep going more and more and more. And when you open it, then it'll put a really high voltage, a very high voltage across that. So the idea is, if you here, the closer you get to having it be always closed, the closer you'll get to a very, very high voltage. And if it's always open, of course, it'll just have the same voltage as this thing. So again, it's a similar kind of intuition here. We're not going to go through the derivation. It takes probably a whole class to do each one, to go through. Well, at least if you haven't seen it before, it would take a whole class to go through each one. So we're not going to really cover it in detail. But essentially, it's good to know that by using these fast switches, you can, in fact, step up and down DC voltage, at least in theory, in a way that at least in theory has no losses. So of course, in reality, there is some resistance in those inductors. And so there is some loss in these things. They do burn a little bit of power. But in theory here, nothing actually loses any power. And so you're doing conversions with DC power in the same way as you were with AC, essentially, with no losses involved. So we're not going to have any sort of other questions or homeworks about this. You're going to, I guess, use a rectifier on the homework assignment, but that's sort of as far as you really go. But it's good to know these things at least exist. And this is how we do things like step up and down DC voltage. OK, are there any questions about sort of this? Because this is actually the end of this whole power systems unit. I know those weren't, it's probably impossible to figure out what was actually going on with these from my explanation, but hopefully the overall intuition will be enough that if you want to figure it out, you can look up the equation. OK, so let's move on now to the unit on control.
Was that in the slides? Well, like which slide was the last one?
It's in the EPS power system. So remember, power system was sort of a little out of order there, but it's in the second set of slides on power systems, before power flow.
Okay.
Yeah. So that's actually probably important because I did sort of switch the order of those things a little bit. I think the power electronics is honestly a pretty separate unit from everything else. It's mainly just good to know about, and I wanted to do the demo there, so I pushed it off till the last bit. But that's essentially why it was a little bit out of order there. OK, so now let's start our third and final unit of the course. The rest of the course really will just focus on these things, which is about control. So to reiterate what I started to say at the beginning of class, we've focused thus far largely on problems that are kind of static in nature. And this is even the case for things like the machine learning problems, maybe, because the question was really sort of, at a single point in the future, what is the demand going to be? I guess that's sort of a temporal prediction, but we weren't really using it as such. We were using it as, at one point, what will the demand be given the temperature? Similarly, for something like optimal power flow, we were saying here, right now, are the costs for all the generators. How should I allocate power to satisfy all of them? And this is an important class of problems, certainly, these sort of static optimization problems. But a lot of problems that you encounter in the smart grid do have a large temporal component. So we don't have to just schedule things right now. We have to schedule things taking into account what's going to happen in the future. If you want to, and actually, maybe I won't give examples right now because I have a lot of examples coming up. But just suffice to say, as we'll see here, a lot of examples are of the class where you need to take into account the temporal effects. or you'll just get yourself into a very bad situation if you always do kind of what looks best right now. And I'll use the term control to talk very broadly about any sort of task or optimization problems where you have to take in these temporal elements into account. You can't ignore them. The task either fundamentally is about temporal control in systems, or it just, if you don't treat it that way, you wouldn't perform very well on the task that you care about. So, and actually, I'm also talking about it, I guess I'm already throwing in terms from optimization here, things like minimize some total cost. You certainly don't have to treat control as optimization. These things are different. However, most of the control we'll talk about in this class falls into the category of something called optimal control. And this, or approximate optimal control. And this is a formulation which you'll see in a second that is very tightly coupled with optimization. So we're going to think of control tasks as wanting to minimize some objective, just like optimization problems, but wanting to do it in a case where there are temporal constraints to what you're trying to optimize. So you can't just optimize what looks good right now. You have to optimize, subject to the constraints of dynamics of the system and constraints that evolve over time. And just to give a few examples now, control tests really are very common. They're all over the place in energy sustainability problems, right? So for example, heating and cooling buildings would be a control task, right? Because heating and cooling buildings, you cannot set the temperature of a room instantaneously. It's not like you can say, okay, is the room occupied? If it's occupied, then set it at 68. If it's unoccupied, set it at 60 or something like that. I guess this is for the winter. You can say that's the desired temperature, certainly. But to actually heat a room, you have to take into account the fact that the room's sort of air has some thermal mass. And you cannot instantaneously change what the temperature in a room is. So if you're going to think about controlling the temperature in a room, you have to think about a system that evolves in terms of what's the temperature going to be, say a minute from now, given the current temperature and whatever control I have, like a heater or something like that I can turn on or off. That's really the thing you need to think about, the system you need to think about when you talk about heating a room, because you can't just instantaneously set the temperature in a room. The same thing goes with storage of energy, for example. You cannot tell a battery to have a certain amount of storage right now. Just have this much energy right now. You need to actually put it there, right? And so when you talk about controlling a battery, you have to think in terms of this state of the battery. And I'll formalize what I mean by state a little bit more in a second. But you have to think about what you mean by the state of the battery. You have to know that I can't draw power from my battery unless I've charged it with some amount of energy. And likewise, I can't give it some amount of energy unless I take power somewhere to charge it. And furthermore, the energy is equal to the energy the last time minus or whatever, plus or minus whatever you subtract or add off. So this is sort of a system that you have to take into account these almost, it's almost silly to say these are dynamical systems because they're so simple, at least in the ideal case, where this is just an actual energy storage system or an ideal energy storage system. But these are dynamical systems fundamentally. A few more others. We're not going to talk about this one too much, but a lot of individual things like wind turbines or solar panels will actually have inner control tasks, even at this level of a single panel, to essentially ensure that they are always operating at their maximum efficiency point. They try to, at least. They don't always succeed, but they try to always operate at their maximum efficiency point. There's this thing called something called maximum power point tracking. And then finally, one of the big kind of things that we'll talk about is scheduling generation in a grid, but doing it in a sense that actually preserves some sort of temporal continuity. So if you add things to your grid, like storage, like generators that have to spin up very slow, or have to get going very slowly, so they have what are called ramp rates. In other words, they can't go from generating no power to generating their maximum power very quickly. It takes them a long time. In these cases, this is a temporal constraint, right? It's saying that we can't go from generating nothing to generating your full power in whatever your time interval is. You have to do it slower than that. That is a temporal constraint. that you're putting on the system. So all these things have internal dynamics, and it's important to take these dynamics into account if you're going to actually control this system well. And we'll give examples of most of these things, not this one, I guess, but we have examples of all the others throughout the rest of the lectures. Before that, though, I wanted to give some definitions. And essentially what this class is going to do is I'm going to give some definitions, give a relatively straightforward definition of control, optimal control in deterministic systems. And then I'll give a couple examples of solving control problems via optimization. And then, of course, we'll introduce a lot of new issues, and then I'll talk about those in the rest of the lectures. OK, so to start off with, just some definitions again. And again, we're using, unfortunately, a lot of the same symbols we use in, for example, power systems and machine learning. And here they yet again mean different things. It's sort of an unfortunate element of this course, again, that we have this. But these are the notations that each of these different domains we use. So you have to be somewhat familiar with, you'll always see X representing a state. You'll always see U representing control. And it's important to sort of be familiar with those bits of notation if you're working in the mindset of someone doing control. So the state is our first quantity we're going to talk about. And that's a vector, which we're going to say is an Rn. So n is the dimension of the state space. So for example, right, so before I say an example, let me give the definition here. The state, somewhat informally, but this is actually not a bad definition. The state here, it captures all those elements of the system that determine how it evolves, but which the agent, the controller, whoever we are the ones controlling the system, the things that we cannot directly affect. And what I mean by directly affect there is important. Because we can, of course, affect the state. But what I'm using the term state to mean those things that we can't instantaneously, in some sense, switch. So we can't, so for example, the temperature in a room, as I was saying before, it determines how the state evolves. So if the state variable is the temperature in a room, say, well, obviously the room's next temperature depends on what the temperature is right now. So it affects the evolution of the system. But it is not one that I can snap my fingers and change instantaneously. And this is somewhat tricky because sometimes control inputs take not quite, they're not quite instantaneous to change either. But we're going to sort of have that sort of line. It's useful to think about it at least. The state are those things that you can't change immediately, whereas the control are the things that you can effectively change immediately. Anyway, that's state. The next bit that we'll talk about is the control input. This is a vector U in Rm. So M and N here mean different things than you usually will see in, say, machine learning. Machine learning, we always used M to refer to the number of samples and N to refer to the dimension of the input vector. Here, N will refer to the size of the state space, the number of state variables, and M will refer to the number of control variables you have. And these capture the things that also affect how the system evolves. But the control inputs are things that the agent, whoever it is, us, whoever it is controlling the system, can change. And for our purposes, we'll think about them as being able to change them effectively immediately. There may be some constraints there too, but we'll think about them as things that we can directly control. We directly set what the control variables are. So again, the example for the heating system would be, for heating a room would be, the control input would say is the heater on or off? Okay? Because that also will, of course, affect how the system evolves. That will affect what the next state's going to be. I mean, of course, the temperature in a room will be affected by whether or not the heater's on or off. But unlike the room temperature of the room, we can directly control whether or not the heater's on or off. We can turn it off instantly or effectively instantly, which amounts more or less to just sort of pumping some heat into the room that will slowly change the temperature but doesn't change it instantaneously. In addition to this, there will also be cases where there are, and maybe I should have put it on this slide as well, but we'll see it later. There are also cases, and I won't give it a symbol yet, but there will also be cases where there are external variables that will also affect the evolution of the system. We'll see those come up in a second later. But here, at least, I'm not going to worry about those too much. Essentially, things like, maybe I'll give an example. The example would be something like the outdoor temperature, right? But that would also affect how the room evolves. It's not something we can control at all, though. Even with our control inputs, we can't control it, right? So this is completely uncontrollable in some sense. So there are things like that too, but those will come up actually later on when we talk about some of the more equations. And finally, there is what's called a policy or a controller. When we talk to the machine learning people, they'll call it a policy. When we talk to controls people, they'll call it a controller. These are the same thing though. And what this is a function, which I'll write as pi. And pi takes as input state vectors and outputs controls. So what a controller does is it looks at the current state, and given the current state, it specifies some control or some input. Okay, so for example, a simple controller would be if the temperature in the room is above 70, turn the heater off. If it's below 68, turn it on. Right, so a function of the state, and one of these would be, for example, it would be on if x was below 68 degrees, using Fahrenheit here, of course, and 0 if x was above equal to, I just actually, you know what, to keep things kind of simple, I'll just write it like this. Most controllers actually have like kind of a range where they would, depending on what the last control was, they'll actually either stay on or off, pass to make it, to keep sort of the temperature within some deadband. But here's a simple one. If it's above 68, we turn it off. If it's lower than 68, we turn it on. You probably wouldn't want to do that in practice because you'd get the control turning on and off very fast as the temperature kind of did that, but it's a reasonable control law. Okay, so these are sort of the terms we're going to use, and as you might imagine, there are some extra things that we're going to introduce as we go, but these are kind of the fundamental terms that you should have in mind as we talk about the rest of this unit on control. The next thing that we'll discuss here, and this actually maybe even kind of codifies what we mean by control and state variables, is the notion of a dynamical system. The dynamical system describes how the state evolves over time. Right? So what I said before was that the evolution of the state depended on the control in the next state, but the dynamical system actually determines how that actually works. So in theory, you have states from time 1 to time 2 all the way up to the current time, which I'll call xt. And you have maybe the same thing for control. So you have control time 1 all the way up to the control at time t. And in theory, the control at the next time, or the state at the next time, so xt plus 1, could depend on all of these things, right? It could depend on the entire past history of states we've seen, all the controls executed so far, back to the beginning of time, but we'll call it some initial time here for the starting point. In theory, this could be a function. This could be a function of all these things. What's that? But that gets pretty annoying pretty quickly. It's not that easy to sort of really talk about function. I mean, because this would have have to have different amounts of history as an input to this function, different amounts of controls. These kind of functions are kind of ugly here, and they quickly get very complicated too, because thinking about what happened a long time ago in terms of affecting what's going to happen next, that gets kind of complicated. So what's very common is to focus only on what are called first-order dynamics. We're not going to talk about systems like this where all the past states and all the past controls can affect the next state. What we'll talk about, and this is almost sometimes used as a definition of state and control. We're going to talk about first-order systems, and what I mean by that is, at least in the case of say discrete time, where we think about a discrete sequence of events here, in discrete time, the state at time t plus 1 is going to be a function just of the state at time t and the control at time t. Okay, so this is what's called a first order dynamical system, because only sort of the first, the next state is only affected by the current state. So it's only in some sense first order effects. I guess the xt minus 1, that would be second order effects, etc. Now it's important, actually I forget if I have a slide, I don't think I have a slide on this, but it's important to note that this is not that much of a restriction really. Because if the dynamics really depended on, say, the past 5 steps, rather than just the past 1, you can still write it in this form by just taking all the past 5 states as the current state in some sense. Does people see what I mean by that? So say you have a system where this was what really happened, so xt plus 1. I'll ignore the u's for now, but you can just put them in just as easily. So say you had this, xt and xt minus 1, right? So you had a system like this where the state really was affected by the current state and then the previous state. You could just make a sort of new state variable which had both those two things. This would have xt and xt minus 1. And I'm going to claim that x tilde t plus 1 is just going to be now a function of x tilde t. And this is pretty easy to see, right? Because what you do is you just take this element is equal to this thing's before. I'll just write it here. This would be our previous f of xt minus 1, because both these two elements are effectively in this state here. And this next element would just be xt minus 1. Sorry, xt. Because the previous state of xt plus 1 would be xt, right? I mean, that would be the equivalent of xt minus 1 here for xt plus 1. So the point being that you can always, if you have a system that sort of takes a finite history, you can always convert it to a system that is just looking at a first order system. Okay, now this is sort of, are there any questions about this here? Who here has sort of taken a basic course on control before, or has seen stuff like this before? Okay, some. Okay, so this is the form of the equation that we're going to talk about. And so really, in some sense, I guess I said, this can also be used as a definition of what state means. State means all those things that, at least in a first order system, state means all those things that tell you what's going to happen in the next state, but which you can't directly control. So I guess these two things together tell you what's going to happen next, but these are the ones you can't directly set, and these are the ones you can directly set. That's the basic idea. At least in a first order system, you can also think of state and control being almost defined that way. Now this is what's called discrete time formulation for a dynamical system. Meaning that there is a discrete number of time points there, and the next discrete state is a function of the current state and the current control. What you will also likely see is a continuous time formulation, and this formulation here prescribes the derivative of the current state as a function of the state and the control. So, and I guess I won't write the dot formulation, but right now. But basically, the derivative of x with respect to t, which people just write as x dot because it's so common to take that. So we have a community notation for this. This thing is a function of x and u. And I'm omitting the t subscripts there. You can put them in. I typically will try to omit them when I'm writing continuous time and add them when I'm writing in discrete time. But of course, this means the state at the current time, the control at the current time affects the derivative of the state at that same time. But all these things are for a single instant in time, essentially. And the difference here is, I mean, these are different. There's sometimes when it's more convenient to work in one or the other. If you're working kind of from basic physical laws, it's often nicer to write them in continuous time sometimes, because a lot of sort of basic laws of physics come about as continuous time phenomena. They're really differential equations. But if you ever actually solve these things on a computer, you almost, well, not almost always, but you will often want to work in discrete time because computers cannot handle actual continuous time representations. So you're going to be solving them at some discrete time interval anyway, so it's oftentimes more convenient to work in discrete time when you're solving these things on a computer. The important point, though, is that these can be converted, at least approximately between the two, by Euler integration. So people familiar with Euler integration here? Heard that term before? Know what it means? So some people, some not. But essentially, it's very simple. All it's saying is that if I have a system and I want to know what is the state, say I have, this is going to refer to the state at time t. When I use continuous variables and I want to talk about specific time, I'll typically put it in parentheses here rather than a subscript because it really is a function that will take as an input, as input some time and output the state, but don't worry about that too much. So if I know the state at time t, and I know through my dynamical system the derivative of the state at time t, well, the state at time t plus some little delta t there is going to be approximately equal to the state at time t plus the derivative at time t times whatever time delta I had, times delta t. And that's sort of like a first order approximation to the dynamics, right? You just look at the current time derivative, you compute that, and however big of a step you're taking, you just multiply it by that, and you adjust your current state that way. Okay, so this is sort of like a continuous, this is sort of this is an approximation to how these things evolve over time. It's a technique called Euler integration. There are better ones, by the way, but this is a pretty common way of doing this, sort of as a very simple rule for this. Now, what we can do to convert it to continuous time is call, delta t essentially our interval between time steps. So we're just going to make this basically equivalent to xt plus 1. And this is now approximately equal to xt, we'll call that xt, plus the derivative of the state variable at time t times delta t. But this derivative here is exactly what's given by our function. So this is also going to be equal to xt plus delta t times f of xt and ut. Okay, and this is now a discrete time formulation of this rule, which we only had a continuous time formulation of before. So, and you can actually do the same thing to convert the other way. You can kind of look at differences essentially, and if the effective time difference here for this thing is small enough, you can convert to continuous time too. But again, these things will counter both of them, so it's sort of important to understand that we have both of these, but then realize that we can convert between one and the other without too much difficulty here. This is not exact, by the way. This is approximate, right? Because in exact notation, this will change, this derivative will change even after an infinitesimal small amount of time, less than delta t, right? This will have changed, and so you're actually not quite, this is going to be a little different when you move half of delta t, and so you have to take that into account, but for a first order approximation, literally, this is good enough usually. Okay, so now there are lots of extensions of these things too. So we're going to mainly focus on the deterministic case, or at least through a lot of what we do, we'll focus on the deterministic setting. I guess we'll have a little bit of stochasticity too, but there are a lot of possible extensions of this. So a common extension is to the setting where we cannot actually observe the state itself. So what I was writing before is that I was writing that our policy, right, is some function of the current state, and that, say, gives you the current control. And that's what action the controller takes. This is a problem, though, if, for example, we do not know the current state of a system. So say we don't know the temperature, or maybe we know the temperature in one room, we don't know in another room. And the temperature in that other room actually will affect things, how the system observes, because you have heat transfer, stuff like that. So you can't always write a policy like this because you don't actually know what the current state xt is. Instead, what you know is you know it, or what you know is you know some function of the current state, which people typically write as an observation, yt, which equals some observation function, h of xt. Here I'm writing yt as the vector in Rp, and this is called our observation at time t. A very common example actually is given to this, and not related to the smart grid, but a common example is given is if your task is like like on a boat or something like that, and you want to know the current state is your position. You might not know your position, but what you do know is you know the range to multiple different fixed points in a map. That would be a case where you don't know the state. You just know some observations. But if you have enough observations, obviously, you can actually back out what your state has to be. But what can be more interesting is when you don't have enough observations to even actually figure out your state from at one time. You have to use sort of observations over multiple times to figure out what your state is. In a power grid, for example, another example would be a lot of times, if we treat the state of the system as, say, the voltage angles and all those in our big vector you're solving right for power flow, voltage angles, magnitudes, power and real power and reactive power, a lot of times it's hard to know things like the voltage angle, the absolute voltage angle. You might not know that. So how do you control the system if you don't know the voltage angle? That can actually be very hard. And it's actually sort of, this is an aside, but for a long time it was very hard to figure out what voltage angles were, because what matters is the relative voltage angles at different points, right? And so how do you compute that sort of very quickly? It's being done now through GPS clocks, essentially. You get some fixed time reference and you figure out where you lie relative to that. But before you had that, it would be very hard to know kind of what your absolute voltage angle was. Because all you can see yourself is a sine wave. That's great. How do you know how your sine wave compares to someone else's sine wave 1,000 miles away? That's tough, actually. It's a really hard problem without GPS or something like that. But without an absolute clock that you both can synchronize to, this is very hard. So that would be a case where you do not know your entire state. And so if you want to do some control based on voltage angle, for example, you have to figure out a way of estimating it. Another extension we'll talk about a lot in this course is stochastic systems. So what I wrote before is that xt plus 1, and we'll only talk about this in terms of deterministic systems usually. Sorry, in terms of discrete time systems. You can write stochastic systems in terms of stochastic differential equations too, but the notation there gets a little bit nasty, so we'll just do this for the discrete case. But if we have a system like this, xt ut, this is a deterministic system, right? Because what we're saying is that the state at time t plus 1 is uniquely determined by the current state and the current control. And we might not always know this function, but if we did know it, then it would be we could compute it exactly. The reality is this is not the situation of most real-world systems. Due to two reasons, right? Either there really is some noise in the system that there is some randomness there that is injecting some amount of noise, and so our actual next state equals our current state, equals the function of the current state plus some noise term, which we'll call epsilon t. This is typically assumed to be a zero mean random variable, but it can actually have, and to simplify things, we'll often assume things like it's Gaussian. That makes things very simple oftentimes, but it, in theory, can be kind of anything, and if you let it be anything and you let it depend on the state and the control, you can actually sort of describe arbitrarily complex stochastic systems that way. It's important for this class, at least, to know that this type of stochastic system can be very useful even in cases where the true system is approximately deterministic, or very, very close to deterministic. And they can be useful because sometimes, for some systems, even when the true system on some level we believe it to be deterministic, it also may be the case that our model just is not that good. We're not capturing everything we need to capture to make this system truly deterministic or to capture the determinism. And so this stochasticity lets us sort of account for the fact that we may have an approximate model here rather than an exact model. So these come up both because maybe we believe the real world is stochastic to a certain degree, but even if we don't believe that, if we think fundamentally everything's deterministic, these are still incredibly useful because we will want to use sometimes simpler models where this is not always going to be an exact relationship here. There's going to be some noise or some error if we sort of plug in our current values and look at the next value. And finally, sort of separate from this, because it's really a different type of framework more than anything else, is something called a Markov decision process. Who's heard of Markov decision processes before, or MDPs? Okay, it's actually a nice different subset, strangely enough. So these are the way we'll think about them here, and we won't talk about them too much, though we'll mention them a little bit, is these are a type of dynamical system that usually focuses very heavily on modeling the stochasticity in an accurate way. But to do that, in order to do that, and so it actually has completely general dynamics and general stochasticity. They can be whatever, these functions can be anything they want to be. For most of the rest of the class, we'll actually focus on simple functions here where we can sort of express relationships like this in a fairly compact or say linear form, or we'll get to that in a second. But MDPs, they actually express general functions here and general stochasticity. So they can express any function or any sort of distribution of error. But because these are so powerful in some sense, they really aren't very usable for big systems with continuous states where all these are sort of continuous things. And so typically, they are applied to settings where you actually have a fixed number of states and a fixed number of possible controls you can apply. And by that, I don't mean a fixed dimension. I mean an actual fixed number of things. So for example, if you look at the temperature in a room, that's one state variable, but there are really an infinite number of values you could take, right? Because the temperature here could be anything. It's a continuous value that can have an infinite number of settings to it. What you would typically do to convert that to an MDP, again, this is not, MDPs actually can be defined in the continuous state case too, but they are typically used in the discrete state case. So what you would do to convert that to an MDP is actually take all the temperatures and divide them up into some discrete number of, say, bins, where this one state here corresponds to the temperature being between 60 and 61, and this next one is 61, 62, etc. So MDPs are general dynamical systems here. They're stochastic, but they typically apply to cases where you have a discrete state or discrete control. And discrete control, I should say. All right, so that's sort of the introduction to dynamical systems as a concept. Now I want to introduce control, and in particular, we're really going to focus on this class on this notion of optimal control. And optimal control is, the way you define optimal control is you define what we're calling a cost function. So we're going to define a cost function, which is a function that takes as input vectors in Rn, so those are states, and vectors in Rm, so those are controls, and outputs some positive number. This is similar to a loss function, conceptually, similar to a loss function like we had in machine learning. A loss function said essentially, given a true value of our output, how bad is it to predict something? What this says is, given a state and a control, how bad is that state and control? Okay, so essentially it maps, and we're going to assume it's positive just for simplicity. We'll assume it's always a positive number. C, and as I said before, so C for x and u, that would capture what's the cost of being in that state X and taking the control U.
So the controller would be designed to like minimize that?
Well, that's what we're going to get to in a second. So this is the next bullet point here. Is the goal is of optimal control is to find some controller that will actually minimize that. But this is the cost function. Importantly now, this is a cost function that really talks about the cost at one given time. Okay, so it's saying right now, instantaneously, if I am in state X and I execute control U, how bad is that? Okay, the goal of optimal control, and very importantly, it's the goal of, I guess, yeah. So for the purpose of this class, this will be the goal of optimal control, is to minimize the sum of costs over some time periods. Not just the instantaneous cost right now, but the goal of control can be viewed formally as minimizing the sum of these costs. So the goal of control is to minimize what we're calling the cost to go function. So I'm going to write this as J U1 to T. So we're going to pick controls from the first time until big time T in a way that minimizes this cost to go function, which is the sum of all the costs, the sum from T equals 1 to T, C, xt, ut. So we minimize the sum of all these costs from time 1 to time T. Importantly, subject to the fact that our system obeys the dynamics over this time period. So subject to, so really we want to minimize this. And minimize this over our control inputs, over U1 to T, subject to the fact that our controller has to obey, or that our state has to obey the dynamics. So xt plus 1 equals f xt ut. So the way the reason I'm writing it this way, I'll write it a little bit more formally in a second, is that intuitively what we can do is pick control inputs, right? So I want to minimize these control inputs, and I want to pick them in a way that minimizes the sum of all these costs, subject to the fact that our dynamics, these are functions of the state, not just the control here, these are also functions of the state, but subject to the fact that these dynamics are obeyed through the whole time. And it's important to realize that we are minimizing this whole thing over time, not just right now. So for example, we could define a cost for a building heating, say, to say, okay, I would like it to be between 68 and 70 degrees in the winter, say. We want to keep the building heated to that range. But I also would prefer not to use the heater, right? So I actually would also prefer, I'm going to incur a little bit of cost for using a heater. So our input here is U, is the heat, the heating power or something like that, say. It could be discrete or continuous. And our cost is something like, let's give an example maybe. Does everyone have this written down? I don't want to erase it if people are still writing it. And it's on the slides too. So our cost could be something like, the difference between X and some nominal temperature, say 68. You could square it, do whatever you want. That's sort of our, our ideal temperature. Actually, I don't need a thing there. Plus some, cost, some weight, 5, say, times U. Where U here is always going to be positive. U, say, is the amount of power I'm putting in from the heater. So this is penalizing you if your state's too far away from your desired heating level, and penalizes you if you use the heat. Now, if this is your only, if your only goal is to minimize the cost right now, it may be the case that you always want to, in fact, it will be the case that you will always choose U equals 0. Because right now, the best thing you can do for this cost function is just turn off the heat. I can't actually affect the temperature instantaneously, so I'm not going to worry about that. I have no control over this in the immediate time frame. All I can do is turn the heat on or off. So if my only goal was to minimize, and I'll call this, a C of x1, u1, so the first cost there. This would not be a very interesting control policy. I would always just turn the heater off. The point of this, though, is that we don't want to just do that. We want to minimize the sum of costs subject to the dynamics here. And the reason this is interesting is because, well, this state, the evolutions of states will change based on our control actions. So we can do things now that will not affect the state right now, but will affect the state later. And that then looking forward in the long time period will actually guide us towards a good temperature there. Right, so that's the idea of control, effectively, is that we want to take actions that will minimize, or optimal control, that will minimize the sum of costs subject to the fact that the dynamics are constraining the system. And in the continuous time case, everything's exactly the same. It's just you have integrals now instead of sums. This is why we don't work in this quite as much. This can be hard to evaluate sometimes, these integrals here, or at least, I mean, numerically they often are evaluated sort of as a bunch of little sums anyway, but doing it theoretically can be challenging sometimes. Sometimes it actually can work out very well, and it can be kind of this beautiful math that you get from the continuous time case, but we'll typically focus on the discrete time case. So a little bit more formally now. This was sort of intuitively what was happening. We want to minimize over our controls of what happens in the system. But I want to write this a little bit more concretely now. I want to write now our control problem as an optimization problem. And it's important when I write this, you see, that I'm actually minimizing over, formally, I'm minimizing over both the states and the controls. So I'll just write it out again here. So actually, the actual optimization formulation of optimal control is to minimize over the states, 1 to t, and the controls, 1 to t, subject to a bunch of constraints. So first, the sum, t equals 1 to t, c xt ut, subject to a bunch of constraints. The first one is that our dynamics the system has to evolve in the way our dynamics say. So xt plus 1 equals f of xt ut. We might also have some, say, inequality constraints or equality constraints over the system. A common equality constraint, for example, would be to say that the x1 has to equal, I'll just write it like x10 or something like that, where we maybe know what the initial state of our system is right now, so I can just measure the temperature right now. We can't change that, so that one has to be fixed. The rest, we're writing them as optimization variables, but they aren't really going to be variables here because they're going to be determined by these constraints. Okay, so this is very similar to actually like what you do in power flow, right, or optimal power flow, where you let everything be a variable in our optimization problem. But most of those are actually going to be fixed by the constraints of the system. So you have some variables, but they're not really variables, maybe. But if you were to type that into YALMIP or any other solver, it's much easier to write it this way than it is to write it the way that removes all these guys and just writes it in terms of the U's alone. So when we write things like this, we'll typically write it as these both being variables, but with the understanding that these are not truly things you can control. They're things that the optimization problem will determine based on the constraints here. And in general, we'll actually allow for general kind of arbitrary inequality and equality constraints in a general optimization formulation. Now, this is sort of great. This is nice. It's nice. We've converted to an optimization problem. That's sort of something we like to do. But unfortunately, in general, this is still a really hard problem, right? Because, I mean, all these things could be nonlinear here. We have a bunch of nonlinear equality constraints. That was hard enough for, like, the one case that we looked at before with power flow. Imagine doing it for, a lot of other different, more complex nonlinear systems. That could be very, very hard to do. Especially if you have things like discontinuities here. These can be extremely hard to solve if the system is sort of nonlinear in certain ways. Similarly, if you have hard constraints here, difficult constraints here, if you have things like state variables have to be, have to take on value 1 or value 0, Those are non-convex constraints, so they're very hard to express sometimes. And so this, we're sort of, I'm not going to write those two, but of course these two things are also in our formulation. It's great that we can write it this way, but unless we have a very specific case of dynamics, it can be hard to actually do anything with a formulation like this. And so, of course, most of what we'll focus on here are a bunch of special cases to this where we actually can solve these things efficiently. And there are enough of those to make those interesting in and of themselves, actually, because we actually can solve a lot of problems that seem very complex, but do it still very efficiently. In particular, we're going to focus, I guess I say today here, but I really mean tomorrow. We'll see in the examples. We're going to focus on a specific case of dynamics that is, in fact, typically easy to solve. So if you look at this problem, remember, if you remember back from our sort of introduction to convex optimization, what I said was that problems are, in effect, in some sense, easy to solve if we have convex objectives and constraints. Right? If the objective and the constraints are convex. That was sort of the criterion. Again, there are exceptions, of course, but those were the easy problems. The problems that things are non-convex were the hard problems. So the only way for an equality constraint to be convex is if it's affine, right? It has to be linear, or linear plus some constant term, essentially. So the only way this dynamics here could be convex is if this is actually a linear function of xt and ut. Okay? Similarly, all these things, the cost function, for example, has to be convex. The constraints, these have to be affine constraints, and these have to be convex inequality constraints too. So we'll focus on the case where everything here comes together to make this problem convex, to make it so we can solve it efficiently. We'll focus a little bit on some slightly more difficult problems, but for now we're going to focus on this convex case. So in particular, these dynamics here have to be of the following form. xt plus 1 equals a times xt plus b times ut plus some little a sub t. I guess they could also, these could be time varying if we wanted to, but I won't worry about that quite yet. So this is what's known as a linear dynamical system, or maybe an affine dynamical system. Essentially, if everyone knows what the difference between linear and affine is, linear is just this. So a linear function, it says that y equals cx, and an affine function says y equals cx plus b. That's the only difference there. Affine is you have an extra constant term too. Sorry, maybe we didn't define those terms. But they're both still convex. Linear or affine systems are both still convex. So this is a class of systems, which, I mean, technically it's affine, but we'll call them linear dynamical systems as well. This class of systems here is very important because it says that the next state is related to the current state and current control in a linear fashion. Here, well, we can figure out what size they have to be, right? So xt and xt plus 1 are both in Rn. So this is Rn. This is, I'll just write like this. This is n by 1. This is n by 1. This here is m by 1. And this has to be, I guess, also n by 1. Otherwise, it wouldn't add up here. So from this definition, actually, we already know the sizes of a and b. For this to make sense, a has to be n by n, and b has to be n by m. Okay, so this is a linear dynamical system here where a is a matrix in R n by n, and b is a matrix in R n by m. Now, and I think we're unfortunately not going to be able to get to it today, but it's actually be even simpler in the next class because we're going to worry about one-dimensional systems. And so in that case, this is just a number. This is another number. And so things are very simple. We'll shortly after that talk about systems that are more complex that have many states, but we're just going to worry about one state for now. Things are very, very simple. And the nice thing here is that we really can, again, just take these things and plug them into an off-the-shelf solver like YALMIP to solve fairly complex control tasks. I think this is my last slide before building for an example. So I'll just give a preface to this example in a second, and then we'll actually do it next time in class. The preface to this example here is that we want to maintain temperature in a building in order to have it sort of in some comfortable range. So we want the temperature to always be within these two, within the green and the green and red line here. And so what this corresponds to, of course, is that at the time where it's narrow, maybe the room is occupied, and where it's wide, the room is unoccupied. So we don't care what temperature actually is below, or at least outside of a certain range. There's also an external temperature that will actually come into factor in this little AT here. That'll be some external variable that affects things. But we can set up everything here in terms of one state variable, the temperature in the room, and one control variable, which is the heater in the room. And given that, we can actually optimize some function. In this case, we're going to optimize the cost of electricity, assuming the electricity kind of varies in cost over the day, to maintain comfort in the room, keep the temperature within these bounds while minimizing cost, the cost of generation. And so that seems maybe pretty simple, but it turns out even this sort of simple example creates a lot of behavior that is actually quite complex, what will end up going on here. So we'll get to it next time, but this is an example of a linear system, and I'll show you how it is a linear system, and then we'll talk about how you solve it with optimization. Are there any questions before we rush off? Okay. Well, see everyone next time.